Hi everyone, my name is Tianrui Guan, a PhD student at University of Maryland, College Park. Today I'm presenting my work, VINet, Visual and Inertial-based Terrain Classification and Adaptive Navigation over Unknown Terrain. The work is done as a summer internship project at Baidu RL. The first contribution of our paper is that we propose a novel terrain classification setting and navigation-based labeling such that the evaluation benchmark is not limited to vision metrics, but also for better control and navigation outcomes. We propose a novel terrain classification network, VINet, which fuses visual and inertial features of the terrain. We propose a novel fusion scheme, which closes the latent embeddings between image and inertial data, and an IMU denoising strategy to process noisy IMU data. We deploy VINet on a tracked robot and propose a novel adaptive control framework enabled by VINet with navigation-based label generalization. The motivation for creating label under navigation context is that semantic-based labeling is unambiguous and has limited capability in describing terrains. For example, a three-class predictor for grass, carpet, and concrete cannot make a meaningful prediction on an unseen terrain. In addition, semantic labels may not be directly useful for navigation unless we make some heuristics or rules manually. A navigation-based label is a descriptive label of a terrain under navigation context. To correctly predict a navigation-based label, the network should output a label that will optimize control and navigation decision regardless of its semantics. In another word, the network should aim to make meaningful generalization based on known terrains and benefit downstream navigation tasks. On the left, we can perform supervised training on known terrains, but none of the output will be meaningful if the terrain is unknown. On the right, we propose a navigation-based label such that each unknown terrain is associated with a known label. We added MU and control signal to the network input with the intuition that we will rely more on previous navigation experience on known terrains when we see an unknown terrain. Let's clarify some terminology first. Known terrain is terrain that we can access for getting the training data and fine-tuning an NMP controller. Its terrain label will be based on semantics. Corresponding controller of a terrain is an NMP controller that is fine-tuned on this terrain. We only have corresponding controller of a known terrain. Unknown terrain is terrain that we can only access during testing time or for evaluation purpose. Their terrain labels are unknown because they are not in the training set. For evaluation purpose, we obtain the label of an unknown terrain by testing the controller accuracy of each controller. We assign an unknown terrain based on the best controller on the surface among all controllers that are fine-tuned on each known surface. Here we show the ground truth label for each terrain class. In this slide, we show an example of why we want to output P1 concrete controller on a rocky surface, which is unknown. We run each controller on this rocky surface multiple times and obtain the overall root mean square error. Ideally, we want to switch to P1 controller on rocky surface because it has least tracking error and can lead to more accurate control. Note that in the real world, we don't have access to unknown terrain and would not test each controller to know its ground truth class. For evaluation only, we assign each unknown terrain a corresponding label based on collected data. In this slide, we show the proposed architecture, VINet. Our proposed network consists of two branches, an image branch and an IMU branch. We use efficient net B0 as the image backbone. And for the IMU branch, we present a novel attention-based IMU denoising module. Each branch acts as a feature extractor and maps the visual and inertial data to a shared embedding space for the final prediction. The goal is to make sure the prediction is robust on known terrain and can generalize well on unknown terrain. Here we show the hardware diagram. We use a JSON AGX Orin to run our network and use the Arduino to communicate with the motor. Here we show an overview of our framework. We use the image and IMU that are either previously collected or obtained in real time as the input for VINet. Given the output prediction of VINet, we adjust and choose corresponding NMP controller for navigation. In our setting, the 5 terrains are known and the rest of the 6 terrains are unknown. In this slide, we show the comparisons between our proposed method and some of the baseline methods. Our adaptive control can change controller based on terrain types from visual and inertial input. In this case, the artificial grass is unknown. Note that instead of predicting artificial grass as grass, which is most visually similar, our method predicts carpet controller, which has the best navigation result. The carpet controller have large overshoot on soil terrain, causing zigzag behavior during navigation. The mulch baseline controller has a slightly larger tracking arrow than our adaptive controller. Thank you for watching and feel free to reach out if you have any questions.